Okay, so in module 3, we are going to learn about lipids, which means that we are going to talk about all the different classes of lipids, what are the important members in each class. You will see there is a lot of variety in lipids. We will talk about different structures, and soaps are also derivatives of lipids, when it interacts with sodium or potassium. And also we'll talk about what is their importance in body. So that's something that we are always work with. So you must have done this in last module, and I hope that everyone is understanding the content a little bit better. In lipids, what we are going to do is we are going to start by talking a little bit about, as we always do, what is their importance in dental hygiene. So you can actually read through the slide in more details, just that there is the lipids are also a part of tartar. So, this is something that directly concerns people who are working with teeth. And saliva of people with heavy tartar, it all contains even more than 50% lipid. So there is a lot of lipid, and we need to understand what actually makes up the lipid. What is it, that what are the functional groups that are there? What is the what is that diversity that we are talking about? So we are going to just start by talking about basic definitions. And for that, we need to learn the difference between polar and nonpolar. And so let us just start with this definition. So polar means unequal distribution of charges. So the molecules that have unequal distribution of charge are polar, whereas the ones that have equal distribution of charge are nonpolar. So what do I mean by unequal? It means, in a way, asymmetric. Also, those molecules are soluble in water, whereas nonpolar is symmetric and it's insoluble in water. So I really thought of some of these examples that might help you. If you see here on the left-hand side, this ball, or, the way it is asymmetric, the sign of the company Apple, that is asymmetric. And this boy, this haircut of this boy, that is asymmetric. So these are all reflecting polar. And how is that reflecting polar? So look at the hydrogen chloride. If you remember in the periodic table, do you remember that chlorine is like really, really desperately wants to get one more electron, and hydrogen gives it. So hydrogen is slightly positive, chlorine is slightly negative. So they have this imbalance. Hydrogen is a little bit weak, chlorine is a little bit like heavy. It's like trying to sap out the electron from hydrogen. So this unequal kind of distribution of charges makes this polar. Similarly, with ammonia, when there is N with 3H, you can see that all of them are trying to give to N. That means that these three are different from N. And so there is a lack of symmetry. And in the last one, when there is methyl chloride, you can see that there are 3H and Cl. And that's what makes it, asymmetric. So you can see that that difference. When we talk about nonpolar, you can see that they're all three things are equal. Okay, and this in chlorine, all of the four are equal, and that's what makes it symmetric. Okay. So this is the basic difference between these two. And in this case, you can see the examples in the bottom, like whether you see from this side or that side, the ball looks kind of same, and the apple is symmetric. If you cut it from the middle, it's just the same thing. And this boy's haircut this time is symmetric. So this is all nonpolar. So nonpolar, not soluble in water. That's a good way to remember. Nonpolar, not soluble. Polar, soluble. And one of the things that I always remember is an example of sodium chloride, NaCl, Na plus Cl minus, as polar compound. And I know that salt, I always remind myself salt is soluble in water, and I know salt is polar because Na plus and Cl minus are totally two different things. And that is why salt is soluble in water. That's another thing. You can remember using different kinds of examples. You can using different kinds of methods. So one way to remember, like I said, is nonpolar is not soluble. Okay. So let us look at the general definitions of lipids. Lipids are generally esters. So now we come across the term ester. Can anyone remind me what is an ester? We have read about ester. You can even look back at your notes if you have it handy. What is ester and what is amide? And you can just write it on the chat or you can say it by unmuting yourself. Okay, I will wait till you guys can think of what is ester. Actually, it's even shown in this figure. I'm going to write here, ester is, and I don't know, I'll just wait for you guys. Ester. You can look it up. Look up and tell me what is an ester. Okay, good. Does anyone remember what is the functional group in ester and what is that? Like, okay, example. If someone says, what is the functional group in carboxylic acid? COOH. What is the functional group in alcohol? OH. What is the functional group in ester? That's okay. Yeah, that's actually right. C double bond O with an O. And what about amide? Not the amine, amide. What is it in amide? So this is something that very good, very good. So yeah, I agree. That's absolutely correct. Yes, I can see some of the responses here. So COO, not actually in this way, but let me just circle it here. That makes it much, much easier because it's something which is already present here. That's an ester group, COO. That is an ester. You know, you can see those examples in here. Also, that is the one. So here, why did we study all this in module 1? Because so that when we go to other modules, we have an easy time in recognizing this. And just repeating, if for any reason you did not understand module 1 well, I would highly, highly encourage you to go to the tutoring hour on Tuesday at 6 and try to make most of it. So if you are looking here, the amide is actually just CONH2. Okay, it's CONH2. And ester is COO, which is marked here. So these are the two, these are the two groups you'll find often. And, you might want to know how they are incorporated. So that's what we're going to do the next thing, very next thing. So these are the examples: fats, oils, waxes. So you've seen all of that. You've seen fats, you've seen oils, waxes. They're found in plants and animals and everything. Okay, so lipids are shown in this example with polar head. So by that, what do we mean here? We mean that lipids typically, they are a part of a cell membrane. And here we have, this is just an example. We have these balls attached to these, like whatever you call them, almost feels like a ribbon or a thread or whatever. So these are the polar heads, and this is the hydrophobic or the non-polar tails. So what do we mean by the word hydrophobic? We have suddenly brought in two new words, hydrophobic and hydrophilic. So does anyone know what is hydrophilic or what is hydrophobic? Does anyone know that?
I think hydrophobic doesn't mean it don't like water, and hydrophilic is attracted to water, something like that.
Absolutely. Yes. So absolutely. So hydrophilic is that affinity to water, and hydrophobic is like doesn't like water. Yet this is exactly how I would define it. So if you see here and you think, so this is a cell structure. So I'm going to just draw the cell. Okay, so let's just put this in perspective. So this is a cell, this is the part of a cell, and then the cell is going on like that. Imagine there is nothing inside. Sorry. It kind of goes like that. And so this is the cell. It's still going and still going here. Okay. So the top and the bottom. So the cell has this kind of bilipid layer throughout. Okay. So the question is, why does it need to have like this watery, like water loving thing on the top and water heating thing on the middle? Like, is there an advantage that cells have that kind of thing? And all your cells are like that. So, I mean, this is how your body is. What is the advantage of having hydrophilic on outside and hydrophobic on inside? Now, let me change the words also and say polar on outside and non-polar on inside. Remember, non-polar means non-soluble. So the inside is not soluble. Why should it have inside that is not soluble? Is there an advantage to that? Even if you have never read this before and you can come up with a random reason on your head, you should just share it. Okay, keeps it balanced. Okay. Um, I, I would say that this also changes how many things can enter the cell. You don't want like everything to enter the cell. You want to limit that traffic. Cells should be able to regulate what enters and what doesn't. So having that a big chunk of insoluble thing all throughout kind of helps in that. And having something soluble on the top helps us survive in the environment. If it is so scared of water, then it's not going to be able to hold on to that particular structure because everything outside is primarily water. So that is the reason, and that is the importance of lipid, that they are a very important part of every cell. Um, so what are the different kinds of lipids? So I think when I started preparing the material for your class, which is like last year, I was seeing that, how different ways in which lipids can be defined. So they can be defined based on chemical formula. There is waxes, triacylglycerols, glycerol phospholipids, sphingolipids, steroids, and eicosanoids. So these are all the different types. Okay. So these are all the different types of lipids. But I thought one thing that could be easy, oh my gosh, there's still that error. One thing that could be easy is lipids can be defined in terms of, so I thought this would be so cumbersome. Like it's so hard to remember all these different types. What is waxes with triacylglycerol? There are like 6 different things. And then there are all these different kinds of partition even within the sphingolipids. So that I think maybe a better idea is based on function. I think we all remember function, and I apologize, this definition here needs to be changed. But let's just focus on the green parts. So lipids can be used for storage. They can be used for structure. They can be used as signals, cofactors, and pigments, which is actually very, very interesting. So what we are going to do now is focus on storage first. So I think this is a better way to remember what are the lipids that are used for storage, and they actually make a chunk of some of the cells. So we want to understand that a little bit better. So let's talk about storage lipids. So as we talk about the storage lipids, we are going to first focus on fatty acids, and fatty acids are carboxylic acid. So if you guys remember, so that's why it's so important that we all want to learn the module 1 really, really well. We have seen this word, and I urge you to keep your prefix and suffix table either printed out or next to you when we are studying some of these things. So fatty acids are carboxylic acids, RCOH, and they have long chain of carbon, and they're even number carbon. There is 4, there is 6, there is 8. So that's a long, long hydrocarbon chain. And so why is it hydrocarbon? So remember, there is hydrogen and carbon, and that's what makes it. So essentially the job is storage. When there's fatty acid, that's the main job. It's used as a storage molecule in the body of of animals, um, and even in plants. And then this one right here, this is right here an example where you have this long chain carbon with COOH. So that's what it's going to look like. Now let me see if it comes up. Okay, I do want to say here that there is a skeletal structure that you will start seeing. So I just want to tell you that in skeletal structure, each C is represented by just one dot, and it would literally become like this, you know? So that's what something for you to think about. You don't have to necessarily remember at this time. It's something to think about. So any questions so far in terms of like what is polarity, non-polarity, and how does that influence solubility? And or any questions in the definition of what is a fatty acid like? Let me see here. So this is goes like that, and then OOH. I was just trying to make it for you. I thought by the time you guys are thinking of anything to share.
One quick question.
Yes.
So you said polar would be equivalent to hydrophilic?
Yeah, that is absolutely correct.
Okay.
Yeah, polar is hydrophilic. Yes. So this is how a skeletal structure would look like. Do you know why we draw skeletal structure? Because you are going to draw, maybe need it only once, but those people who are working with lipids and their entire life, I mean, they're going to be drawing and they get tired of drawing all the H. Like, how many times are we going to draw that? So just, do it like this. Yeah, the recording will be posted. But I do want to encourage you guys to ask me questions, especially I want to say, especially if, let us say, we are on slide number 6 and you are feeling like slide number 5 was unclear, you should immediately message me and say, I feel lost. Because I don't want you to sit through everything and think that wish I had asked that clarification, then it would become easier. And I'm telling you that could be a common question that others have. So don't hesitate. You're actually doing a favor by asking a question or clarification. You're doing a favor for everyone, not just yourself. Okay, so fatty acid. Fatty acids can be of different types. And I think this part is pretty fun, even though the names seem like big and all, but I think it's very fun. So one is saturated fatty acids that have single bonds. They do not have any double bonds. By that I mean, please don't count this as a double bond. This is a functional group. We are talking about the chain. And so it has no double bonds at all. Unsaturated fatty acids can have one double bond. Polyunsaturated can have many double bonds. Okay. So this has no double bond, which is the saturated. Unsaturated can have one, and polyunsaturated can have many. So why is this fun? You will see very, very soon. There is so much examples that you can find in your own kitchen that I really like about it. Okay. So let's look at this again. So what we are doing, we are taking the same, yes, question. Is there any questions? Okay. So we're taking the same chain and just making it look different. So we are making it look like this. It's the skeletal structure. Like I told you, sometimes they'll start showing the skeletal structure. And that is the for the saturated fatty acid, and this is for unsaturated. So, oops, no, I went far. Okay, so there is a kink because of unsaturated. Do you see that? Now you guys are really, really smart. So you are going to help me in telling me whether this is cis or trans. When the H is on the same side, whether it is called cis. Cis, perfect. So you know that this is cis, and that's a cis fatty acid. And what happens is when there is a bond like this and H and gets imbalanced. Gets imbalanced, and imagine many, many molecules like this. Okay, so let me just draw this here. So one is like this and then like this, and its friend, another molecule is like this and like this. And then I'm just saying like how they're different orientations. So as a result of which they cannot form a compact structure. This one in contrast, the stearic acid, which I'm going to draw in pink, is going to be straight and going to be straight and going to be straight and going to be straight. So everything here is very, very compact. They are very close to each other. It's a very close structure. So in your kitchen, you have butter and you have oil. Which one seems to have a very like a flexible kind of structure, and which one seems to be at room temperature? Which one seems to be a rigid structure?
More flexible.
Which one is flexible, you said? Or oil? So oil is flexible.
That's what I was thinking.
And then butter is not flexible. Butter is more like solid, right? So why is oil flexible is because it is, it's unsaturated. It is unsaturated. So it's all molecules are very wobbly. They're having the double bond, which kind of doesn't let the structure put in kind of close to each other, as a result of which they are unsaturated. Okay, cis and trans. Yeah, okay, great. So cis and trans is very easy concept. I'm going to tell you something here. Okay, so let us see that there is a double bond here, and I'm going to make one more over here. C, double bond C. So by cis, I mean, like, let us say there is cis is on the same side and trans is on the opposite side. So first, let me draw that. So I'll just write here, cis is when a certain group is on the, it can be anything. So in this case, it is H. So let me just show by different examples. Suppose there is chlorine, and chlorine is on the same side. There are two chlorine molecules, atoms, and they both are on the same side. That would be cis. And if it is on the opposite side, so cis is same as, it is same side. And trans is opposite side. Oops, opposite side. So if you see things that are on the same side, like in this case, if you see H is on top, the second H is also on the top, same side. However, if we took this H and put it down, then that would be a trans. Is that okay? Or you should also ask a specific question if that's not okay. So same side is cis and opposite side is trans. That's how we define it. And in this case, like I said, H is on the same side. That's what makes this cis. Okay, great. It's very good question. You know why it's a great question? Have you heard about trans fat? Without going to the other slide, can I ask you, have you heard about trans fats? Like, these are the things that blah, blah contains trans fat, which is not good for your body, right? So if you've heard of it, try to think, what are those things that are having trans fat? Okay, we're going to come back to that, but think about it for now. So in general, saturated ones have no double bonds. And that's, again, a very important assignment as well as exam question. And then they look straight, they're looking straight. And what is this little ball in here? That is the COOH. That's a carboxylic. That's blue because that's kind of not same as carbon, right? So we just wanted to distinguish. Whereas the unsaturated one is a little bit fancy. It's almost like it's dancing and it's like hitting each other. So it's so dynamic, as a result of which it is more like oil. It's the oils are the ones. So less stable aggregates, and that's why it is going to be in the form of an oil. Okay. So saturated fats stable at room temperature due to tight packaging, just like solid like butter. So whenever you're eating butter or using butter in baking or anything, you should remember you're using a saturated fat. However, any kind of oils that you use that are unstable at room temperature, and because of this kind of packing, that is unsaturated fat. It keeps moving. So think of more fats that you use in kitchen, and are they saturated or unsaturated or trans fats? Okay, so this like nice little figure so that I could introduce you to this topic, which is a little bit mundane. But then when you see this figure, you can say it's not that bad actually. So we're talking about saturated fat, trans fats. Yeah, literally, trans fat is bad for you. Polyunsaturated fat, PUFA 3, PUFA 6, and monounsaturated fatty acids. So all of these meet the fat. Some are bad and some are good for you. Okay. So review. What is saturated fatty acid? Single bonds, there is no double bonds. Monounsaturated or unsaturated fatty acids with one double bond. And poly has many double bonds. It can have one, two, it can have two, three, four, whatever that amount is. So important thing to know. Now you may think, what will happen in case of poly? Like when you are making structure, of course, it's going to be really dynamic. It's going to be like really wobbly. It's like almost like a drunk person moving around. So it's going to hit everything. It's going to be liquid, of course. So now comes the interesting part of how to name a fatty acid. It looks complicated. It's actually very easy. It's not at all complicated. So I need you to be 100% focused when we are talking about this. If we are doing something alongside, let's just focus on this next 2 or 3 slides where in just single mind, okay? So you look at this acid. This is an unsaturated acid. The reason it's unsaturated is because whenever we see a double bond, we know it's unsaturated. That's a double bond. So first of all, is this skeletal structure okay with you? I just want to write down, a little small notes for you here so that it makes it more sense. All of these corners are C's. I'm going to make it C here. I won't be able to make for all, but I just want to remind you, these are all C's. All the corners are C's. Now you may say, what happened to the H? Everything is there. You're just not representing it here. Okay. So let's do the H by blue lines. There is H here. There is only one bond. So 2, this is 3. This has already 2 bonds, 1 bond, 2 bonds. So there's 2 more. This is 2, so this is 2 more. So like that, it kind of goes on. It's not like we have left it. Okay. But how do we name it? So the first thing is in nomenclature, count the number of carbons. So you start from this end, 1, and then second corner is 2, third corner is 3, fourth corner is 4, and so on and so forth. You keep counting. Don't worry about the double bond. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you've reached 18. I don't expect you to remember this octadecanoic acid. So which means I'll give you this thing. You don't have to even think about that. But what I expect you to do is able to count properly and then put it over here, 18. That's all. It's not that hard. So you put 18 for the number of carbons, you put a colon, and then you put the number of double bonds. So how many double bonds are there? Don't count this. I'm going to mark this. Don't count this. Okay. But do count this one. So let me mark this with the tick. I have a tick in Zoom. Yeah. So count this. Don't count this. Okay. I'm going to, so this is, we know only, there is only one. So we put it over here. And then delta indicates the position. Position of what? Delta indicates the position of the double bond. So position of the double bond, it starts at 9. So we put 9 here. So, and it is, you don't have to worry about cis at this point. All you need to worry about is this front part. Okay. And that's what is written over here. So what is the procedure? Count the number of carbons starting from the COOH group, count the number of double bonds, and go to the position. So count the position at which the double bond is present. So this is the 3-step process. Okay, I know someone joined a little bit late. So I'm, for their benefit and for the benefit of the entire class, I'm going to repeat this whole thing again. And I need you to stay focused, okay? So how to name fatty acid? 3-step process. First step, count how many carbons are there. And always remind yourself, each of these corners are carbons. This is a carbon, this is a carbon, this is a carbon. Why is it not written? It's just tiring to write CHH at all points. It's kind of obvious. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. Okay, so that comes in the first, in the front, colon, followed by how many double bonds are there in the carbon chain, not here, don't count this. One double bond, delta. What position is this double bond? Number 9. 18 is to 1, delta 9. Your job is done. Any questions from this particular slide? I'm sure there may be questions. So, I mean, we are going to
practice one.
Say that again, Crystal.
Can you do like another one, like another?
Yeah, let's do it. Yeah, exactly. Yeah. Good point. That's actually what we're going to do now. Let me clear. Okay. Sorry, this looks a little bit more. Let me see if there is an easy one. 1, 2. Oh, we can actually go back. Let's do this one. This is not done, right? Let's do this one. So we have to count. So as I go through it, you can help me count. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. Actually, this is also number 9. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This turned out to be the exact same example. So when I see this, assume I don't know that. So I'll just say 18 is 2. How many double bonds are there? 1. What is the position of the double bond? And I cannot make the delta sign. What should I use instead? I don't know. I should probably know a way to make it, but let me just write delta because that's what exactly it is. Delta, and then position number. Let's count the position. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's right, Gina. Yeah, that's exactly what I was getting to. 18 is to 1, delta 9. Yeah, but we will have a chance to do a more complicated example very, very soon. That is like literally the next slide. Okay, so before people can see this, let's hide this. Hide it, come on. Okay. All right. Yes.
If let's just say might be a weird question, I'm not sure. Let's just say there's no double bond. What will we put there?
Nothing. You can just say 18. I mean, you probably don't even need to do the numbering at all then, because it's obvious. It is already included in the name then. You don't have to do anything. So that is why this nomenclature thing is only for, only for unsaturated. So you don't have to do it. And like I said, I never asked you to do eicosapentaenoic acid. Oh my gosh, please, I'm not asking you to do that. So that's like, okay, hold on, my power is gone. I'm going to get my charger, but in the meantime, you can see the carbon, count the number of double bonds and the carbons, and then we'll do it together. I'll be back in a second. Okay, 5 double bonds. Okay, great. So let's do this slowly. Very nice. Okay, I have an answer. Yeah, that's pretty much how you would write. So let's check it since we have an answer. So let's check it. But before that, let's just do it like, assume some people are having a little bit of trouble because it's crazy stuff, right? Okay, so The number of carbons is counted for me, so I'm not going to be worrying about that. But I do want to pay special attention to double bonds. Okay, so whatever number is on the top is the one that is the carbon corresponding. So 5, 8, 11, 14, 17. Okay, so that's great. So I'm going to check this now because I think I've verified everything. Okay, so it is 20:5 delta. So 20, number of carbon, 5 is the number of double bonds, delta is the position, at position 5, at position 8, at 11, at 14, and at position 17 are 5 double bonds. And so this is 20:5 delta 5, 8, 11, 14, 17 eicosapentaenoic acid or EPA. Okay. So one fun thing in chemistry is that very long and complicated name. So I think you should take this as a dare. Okay. Yeah, I'll tell you the purple numbers too in a second. You should take this as a dare and try to just say the names, like literally, sound it out. And, at some stage, like I remember that, of course, we all have hesitation saying things, but when you are a teacher, you don't have that option. So I do remember that while I was teaching, whatsoever complicated the scientist's name is, I just had to say it. So just say it, eicosapentaenoic acid. Okay. And of course, sometimes my accent or my way of saying may be different. That's fine. You can just say it your way. Okay, now, so good question that Emma Beth asked me is, what is the purple number? So yeah, that's what it is. I think you will be able to relate to purple numbers. So you know how we started counting here. Let's start counting on the other end, and you will see the reason soon and see because we want to find where the first double bond is. So when we count from here, we call it another fancy name, and that is omega. So omega 1, position 1, 2, 3. We said omega position 3, we have the first double bond. So we call it omega-3 fatty acid. Have you heard about omega-3 fatty acid? They say, oh, you should always take omega-3 fatty acid. You should have omega-6 fatty acid and all that. Yeah, so when they say that to you, this is exactly what they mean. This is the omega-3 fatty acid. By that, they mean this is the kind of nomenclature they mean. So they are needed for, people will tell you, hey, you should have fish, salmon, and all that. There are lots of good omega fatty acids. So that's exactly what they mean. They mean that this kind of nomenclature in which you are counting from the methyl position, this is the methyl position. Now you'll say, what is methyl? So if I could remind you, please, that this is a C here in the end. And then the C is attached to 3 hydrogens, right? So I'm just going to draw it briefly by saying there is a H here, there is a H here, and there is a H here. So this is not methane, methane is CH4, but methyl is CH3. So when you're counting it from the methyl position or this farther end, the first double bond that you see makes it the omega-3 because it's on 3rd position. If this was not the first double bond, and this was the first double bond, you'll just call it an omega-6 fatty acid. Okay. So,
oh, sorry.
Yes. No, go ahead.
So I have a question. So basically, all right. So how we counted the carbons, and then we counted the double bonds, and then we counted the location where the double bonds is. So this is technically just the next step. Like you will have, okay.
Absolutely. So this is the last step if you're having that omega nomenclature. Yes. You can call it omega or N or whatever. Scientists like to have all these different names because they are studying it in a different way. And so they need to have, a different way of naming them. And it is also easy, you can, like if I told you that, hey, you need to have omega-3 fatty acid supplement. Instead, I told you, hey, you need to have 20:5 delta 5, 8, 11, 14, 17 eicosapentaenoic acid. You'll be like, what in the world is that? So this is just an easier way of saying that it's a polyunsaturated fatty acid, and omega-3 is the first position of the double bond. So just making it super clear, easy, in terms of,
That's how we would write it, with the N slash.
you can
Okay.
write W. W is actually here omega. So let me write that for you. That would be omega 3. Yeah, that's it, omega 3. So you can write W3, that's fine. On the top, on the, at the end of the parenthesis, you will literally write it like that. And that should be fine. What I will never ask you, like I said, I will never ask you to remember eicosapentaenoic acid. That's not something that it would be wise to memorize. Then your memory is being spent in a wrong way, memorizing stuff. Okay, so this brings us to cis and trans fatty acids. So, you know, cis and trans, cis is on the same side, trans is on the opposite side. That's the cis and trans we talked about. How are these actually different? So let's see. Try to see. Okay, so you know this trans. Let me just draw this over here. Trans, it's pretty straight. So tell me, what does this remind you of? We draw this before, you know? We have drawn this in a couple of slides before.
Saturated.
Yeah, this was reminding me of saturated. Hey, this is not unsaturated. That's like, these guys, they are like hitting each other and bumping against each other. That's like what happens to stuff in liquid. This one is straight and that's saturated. Now, that actually may not be good for the body. Let us see how. Okay, so look where the trans fat is. All the things that you really, really like. Oh my gosh. The processed snacks, the fries, everything is like trans fat. And trans fat, you know, it's hard for the body. It's not easy for the body to process that, right? So saturated fats, trans fats, these are the ones that tend to remain solid. They are the ones that raise cholesterol and increase heart, disease risk, and their intake should be low. There is monounsaturated, avocados, olives, nuts, fish, vegetables. All of these are better for you because they have those things that are not that tightly packed. You can imagine, like, if you're having butter, your body is like, I mean, you like it obviously, but your body is like tough time breaking the structure apart. Like, it's just having a really tough time. And also there are other impacts on the cell, not just like it's about breaking the bond. So you can see that all the things that we really, really, sometimes crave for, like fries, those are not actually good for you. Those are the ones containing trans fats. So what actually does that mean? So what happens is that when we are having a normal diet and it's a normal cell, then low density lipoprotein, it causes this, it takes the fats into the cell, okay? And the high density lipoprotein, it carries the impurities out of the cell. So that's good. Good to know that. Now, what happens when you have unsaturated stuff? Well, the bad, I think it takes the stuff that is bad, like it's the same size of the like, little truck is same, the pink truck, or maybe a little bit smaller. But the high density lipoprotein, like it can carry way more impurities out of your cell, okay? So it drives it makes the cholesterol lower in the blood because of that reason. However, so that's a good thing. That's a great thing that when we have unsaturated fatty foods, then, there is lower cholesterol in the blood. Okay. But what happens in case of saturated fatty acids? So it raises the amount of LDL. When it raises the amount of low density lipoprotein, it can carry a lot more fat into the cell, but the cell doesn't want the fat, but it's carrying the fat, okay? However, the amount of unhealthy stuff that's going out is less, which means that it is making the cell, unhealthy and raising the cholesterol in the blood. A similar thing is done by trans fat. It lowers the HDL. So it significantly raises cholesterol amount. So these are the two, saturated and trans fat, which raises the cholesterol And the unsaturated ones, all these olive oils, avocados, salmon, all that you eat, it helps lower the cholesterol in the blood. So that's what is the importance of, um, you know, fatty acids in the human body. So this is how it relates. So let us try to understand in this one chart. So LDL, or low density lipoprotein, transports or it stores cholesterol within the bloodstream. So bad idea. And then high density lipoprotein, it regulates LDL storage and promotes excretion. Okay. So if you see here, the artery, this is low density lipoprotein accumulation. So we don't really want a lot of this. Now remember, the truck has gotten bigger on that side, which was not a good thing. So you don't want too much of this, because what this will cause is it will obstruct the flow of the blood. So let's take a look on this side, and then we will come back to this final figure. Fats and cholesterol cannot dissolve in bloodstream as they're non-polar. So now we are coming back to that polarity discussion. So they are packaged with proteins to form lipoproteins. So what do low density lipoproteins do? So you can see the correlation here. The fats are packaged with proteins to form lipoproteins. So if it's a low density lipoprotein, it carries the cholesterol from liver to body. So it raises the blood level, cholesterol level. High density one, it carries the cholesterol back to the liver for disposal. So, that means that, the scenario where high density was good was really a nice thing. And low density we do not want, but trans fat and saturated fat are hell bent on increasing this, which means that the more and more a person eats the trans fatty food, it kind of clogs the artery, which is not really good for the human health. So that's just the correlation of how the chemistry relates to the polarity, and the polarity leads to how it's soluble, and then how it actually affects your arteries. So just another discussion here, that the humans can synthesize most of the fatty acids, but it cannot synthesize these omega-6 and omega-3 fatty acids, which is the linoleic acid and the linolenic acid. So these are a little bit difference in name. It's kind of hard to spot. Omega-6 is linoleic and omega-3 is linolenic. So this is the vegetable oil and the safflower oil. So that's the one that you probably are using for cooking. And then there is this, there are these green leafy vegetables, chia seeds. That's why, there is so much of, these days you hear so much more on these flax and chia seeds, walnuts, soybean oils. All of these are the omega-3 fatty acids. And the eicosapentaenoic acid, which we're looking, is a fish oil, algae oil, krill oil, all of these. So these are really easier to break by the body. And they're essential fatty acids. And when they say omega-6 and omega-3, it should immediately remind you of our discussion that how we get to the word omega-3 versus omega-6. Okay, so why cannot humans make this fatty acid? Because this is essential, body needs it, because they do not have a certain enzyme. So they must have it from outside. So if you're not having it, body will not have it. If body doesn't have it, brain development is impaired. So especially for moms, for babies, they'll say, hey, they need to take the omega-3 supplement because we need, make sure that the brain growth is good, right? So that's the importance, because body needs it, cannot make it, so you need to have it externally. So here is the complete list, and that brings me to one of the questions that I'm trying to think. Who asked? I think maybe Stacey asked. Someone asked. Okay, so what happens in saturated? There is nothing. Like, you can write it, but there's like nothing. It's 0 double bonds, right? So you don't need to write it. I mean, it doesn't really make much sense. However, if it is unsaturated, then of course you can write 16 as the number of carbon, 1 double bond at position number 9, and so on and so forth. You can write it down. And there is also there is other ways of representing, like omega-3 or omega-6 or omega. Don't get confused by this name. There is different science, different I guess, set of fields would use different names. I think the best way is to think about it more like this is already being in use and we just have to learn it. So it's N or omega is both acceptable. So this is a nice list. It lists everything. Nothing will be asked in the exam like, what is the structure of lauric acid or something? Yeah.
I just completely got confused. Can you please start over, please, on this page?
On this page, yeah. So
Yes.
remember we talked about saturated fatty acids and unsaturated fatty acids?
Yes.
Okay, now we are listing them all, the things that we use. So we are just saying these are our saturated fatty acids with 4 carbon, with 6 carbon, with 8 carbon. You can see the names here, bute, hex, oct, all of these, right? So these are the saturated fatty acid. They have 0 double bonds. You know, saturated never has double bonds. Unsaturated fatty acids are listed below, and these have 1, 2, 3, 4. They have different kinds of double bonds. These are the position. They should have actually written delta here, but like I said, different people will just write in different ways. So actually the good way of writing would be delta 9. And this would be delta 9, 12, comma 12, but I think they just wrote it like this. That's another way of writing. You know, the reason it is important to expose you to different ways of writing is because we can learn in way 1, but if the world is using way 1 or way 2, then we need to learn both the ways.
Right now you're writing the omega. Wait, no, that's not the omega.
Omega is
That's
this one.
Okay,
That's
so I'm so
that's-
sorry. So right now
but
you're
this-
doing the double bond.
Double bond, 16:1, delta
Mhm.
9, and that's
Got
all through the COH end. And this is omega 7 or omega 9 or omega 6. So these are all omegas. They're just written as omega or N. This is an option. You can write it as omega or you can write it as N. So in this one, I think they chose to write as N. Is that okay?
Yes.
Yeah, there's not much strength in your yes. Looks like you like accepted it, but not really. So we will do it again. Don't worry. We'll come to this again. I do want to make sure that today I don't cover the entire module 3 because first of all, I know you guys are worried about the exam and you have other things to do. But then also there is this has lots of topic. Delta is for single, omega is for double. Actually, no, that's not correct. Delta is not for single. Let me just go back to this. So delta is for double bonds, double bond position being counted from this side. So let me just write it here. Sometimes it's really helpful to write delta. So someone asked me a question or a clarification on this one. So I'm just writing delta is showing positions from COOH end. So when you are showing delta, that means you're counting number 5, number 7, also all is from the COOH end. And what is omega? Is counting the first double bond from methyl end, which is opposite to COOH. So that is the difference. So omega is counting it from the right side, which is this methyl end or methyl end, and this one is from the COOH side, which is the carboxyl end. So that is the difference between, but they are both for unsaturated fatty acids. Remember, saturated doesn't even have a double bond. So delta will have practically nothing on the top, no double bonds. If it was a saturated fatty acid, we would make this 0 and we will remove all of this and we'll get rid of omegas. Nothing. It is nothing. It's just this, just 20. 20 is to 0. Is that okay? I hope it's okay.
Yeah, repeat that last part. You said, I don't know why my screen kind of broke up, but you said
Okay,
something.
yeah, no problem. I can repeat it. So what I was saying is, imagine if this has no double bonds, if these are all single bonds. If that happened, then this will become, because there is no double bond, so 0, 20 is to 0. Since there are no double bonds, so you don't need to count all of these. These are going to go away. There's nothing. The delta will go away. And even the omega will go away because omega was for counting the first double bond. So there is no double bond. So it was literally 20. If this has no double bonds, I'm not saying this doesn't have, but if there was no this, let me do this better. And there's nothing here, nothing, no double bond. Then in that case, it is 20 is to 0 equals a pentanoic acid. Because omega and delta are for double bonds only. So there is no double bond, there is no delta, there is no omega. Is that okay?
Yes, thank you.
Okay, good. Okay, so what we have understood here is, so far we have understood about the saturated and unsaturated, and we will do a smaller review next time for this. But look at this. These are the conditions and disorders, or with excess or deficiency. You can take a look at these. These are something that you can read for yourself. And then, though we are not going to do everything, but what we are going to do is we are going to cover the triglycerides before we leave. Okay. So I know that this is a lot of information, but if we do triacylglycerol, trust me, when you come next time and we do triacyl, it will seem so much more easier. You see the same information twice, so much better for your brain. So we talked about fatty acids. Now we're going to do something different. We're going to take those fatty acids that we were talking about so far, all of these fatty acids that we have studied, right? And we're going to do something with them. So what are we doing with them? We are adding them, three fatty acids, not just one, to a glycerol molecule. So what is a glycerol molecule? It's a very interesting molecule. It's CH2CH2 with 3 OH. Each of the fatty acid comes and binds with one of the groups here, COO, COO, COO. And so it is tri-acyl. One acyl is for a fatty acid, right? So you are saying here, I'm going to write here, fatty acid is acyl. All right, so what we are saying here is tri-fatty acid. So we are saying a nice fancy word, triacyl glycerol. 3 fatty acids linked by ester bonds to a glycerol. So what I don't want you to ever forget is these bonds and all, like that's what we talked about, esters. So these are esters. You have to remember that. So we were talking about carboxylic acid, but now we're talking about esters. So triacyl glycerol. What are these blah, blah chain? These are carbon, like that. And I can see there is no double bond, so no unsaturation. So whenever I'm looking at these, I'm always paying attention to these little details, saturated or not, unsaturated or not, all of these. So what happens is there's glycerol, it's a water-soluble alcohol. You attach the fatty acid to it, the water goes away. You have done this before. You've seen how condensation happens in case of when you put 2 glucose molecules together and a maltose is formed, water goes away. You're seeing the exact same thing here. Water goes away and you get this triacyl glyceride. There are different ways of saying it. You can say triacyl glycerol or triglyceride. These are just like you guys have, some of you have different names and people call you by different names, just like that. So there can be simple triglyceride where everything is the same. And there can be fancy ones, the ones that have one fatty acid is different, one is different, another one is different. So all of these are different. So that's simple versus mixed triacyl glyceride. What are these used for? They're used for energy. They're used for waterproofing, for insulation, and for protection. So we will see how in some of the next slides, but I mean, it's understood that if they are water repelling, where especially, you know, what hates water, I'll tell you. These things, they hate water, carbon chains. They have nothing to do with water. They don't like water at all. So they hate water. These things with O's, they like water. So this is the part that likes water. This is the part that hates water. So what happens in human body is that, you know, these triglycerides, they are found to be present, you know, in where the fat storage is. You know, that's where there is a presence, and you can see those now fatty acids or triglycerides and all of that. So so what about oils? So oils are a mixture of triglycerol that is liquid because it contains a high proportion of unsaturated fatty acids. And we talked about this a little bit. We didn't talk, you know, we are going to do, you know, we didn't talk about all sorts of oil. Then there are fats, they're solid because it contains high proportion of saturated fatty acids. So yes, we have done that part. And they can be polar or most of them are non-polar and hydrophobic. They hate water, right? Okay, so let's, so carbohydrates and lipids, how are they different? So we talked about carbohydrates. So we talked about carbohydrate that they used for energy storage. I do want to tell you one thing about the carbohydrate chapter. I think I noticed it when I was doing oral exam. I think people don't remember the second part of module 2. I think there is more memory of what is, you know, chiral means 4 different groups being attached and all of that, and L and D forms, but they have lesser memory of what is a disaccharide, what is a polysaccharide, what is a glycosidic bond. I think so. You must review that before you do your exam. So that's something I want to mention. So carbohydrates have a lot of different functions. They can be easily digested. They are used for aerobic and anaerobic respiration, which we are not going to do during this course, but they're just for releasing ATP. They can, of course, generate ATP. They're water soluble as monomers and dimers and easy to transport. On the other hand, the lipids are long-term energy sources. They have less effect on osmotic pressure because they are not soluble. There's osmosis is to do with water. So if you don't want to deal with water, you're not the one influencing osmotic pressure. They're not digested easily. They can only be used for aerobic respiration, and they store a lot of ATP. So it's important. It's still important for the body. They're not water soluble and are difficult to transport within the body. So we just 2 more slides remaining for today. So triglycerides have typical ester and alkene chemical properties. So I'll tell you what we mean by that. By ester, I mean C double bond O. That's what I mean. So if you look up your table, suffix table in module 1, that's what I mean. Okay, so the one thing is saponification. That's what we're going to do first, and then hydrolysis and hydrogenation. So let's first of all start with the boring part and then get to more fun part. Actually, it's not that boring. You have done the hydrolysis already. So you know what happens in hydrolysis? Lysis on the basis of adding water. Lysis is cutting. You are adding water, you're breaking the molecule. You did exactly the same thing in polysaccharide. You take a lactose, you can break it in glucose and galactose. You take a maltose, you can break it in glucose and glucose. And same thing with fructose. You can break it apart, right? So in this case, sorry, that's sucrose. So in this case, however, you are breaking the, oh, you cannot see the screen. Can people see the screen, guys? Can you see the screen?
Yes.
Oh, okay. Oops, someone cannot see the screen. Oh, okay. Okay, that's good. Yeah, sometimes there is a lapse in internet and all that. So breaking with water always means add water, break the molecule. So you are originally back to glycerol and the 3 fatty acids. That's what hydrolysis is. What is hydrogenation? Very important and easy to miss because, you know, you read so much and then you're like tired. So just reminding you, what is hydrogenation? Hydrogenation simply means adding hydrogen. Where do you add hydrogen? Wherever there is a double bond. Can you add hydrogen to a saturated fatty acid? And I'm already telling you there is no double bond in that. And you cannot add to COOH. Can you add hydrogen? That's the question. The question is,
No,
can you?
right? Because there's no double bond.
There is no double bond. So how can you add hydrogen? Can you add hydrogen to saturated fatty acid? No, you cannot add because there is no double bond. No, you cannot add. But when you have an unsaturated fatty acid, then there is a double bond. You can force it to remove that double bond. You can be like, hey, you know, you need to get rid of your double bond, okay? We're going to put 2 hydrogens in place. So instead of having, so how the structure is, it was like this, oops, and this. And then there was actually, try to see, a double bond in here. And this is still there, right? And this, there is hydrogen in here. That's how it is. Actually not this. So how many these things are there? So this one is, this particular hydrogen, carbon has 1, 2 on right side, 1 on left side, 1 on top, total 4. So now you tell this particular double bond, he say, I need to get rid of you. So what I'm going to put is, instead of you, I'm going to put 2 hydrogens extra, and this will become saturated. So you can actually convert something unsaturated to saturated by forcing it, you know, to have accept 2 hydrogens. You can use hydrogen gas, literally, and a catalyst, and it is forced to convert unsaturated oil to saturated. You can do that. So
I don't know if it's just my computer, but my computer is like super slow with catching up with yours. Like the mouse just keeps disappearing, so it's hard to keep track on what you're doing.
is it same thing with others?
Yeah, is it just me?
Is it just
I'm
Gene?
getting static.
My computer doing that too.
Oh, then it has to be me.
mine
Then it cannot be you guys. It has to be me. Hold on. Okay, does it, is this better now? Is my mouse moving better now or no?
I don't see anything yet.
Oh,
Yeah, there's
okay.
nothing on the screen.
Okay, when it comes, let me know. You know what? I think the computer is tired.
Yeah, me too. I think so.
Yeah, okay. So what we can do is we will start next time from the same point, because if it is not working for some reason, then we need to make sure that it is, it's working. So let me stop recording.